Okay, here is the second NewsELA article for the time travel text set. This one's called Time Travel May Be Possible for Certain Tiny Particles, but Probably Not. And this came from Scientific American, which was then adapted by the NewsELA staff on October 14th, 2014. Okay, visitors explore. This is the caption for the photo. I'm just going to read that for you. Visitors explore an imaginary time machine, part of the Philadelphia International Festival of the Arts at the Kimmel Center for the Performing Arts, March 28th, 2013 in Philadelphia. So this just shows two people at an imaginary, in an imaginary time machine at an art exhibit. Okay, so I do think it wouldn't hurt for us to go ahead and preview the questions at the end like we've been doing. Okay, so let's take a look at that. Zoom those in a bit. So, alright, so there's four. The first one just says select the paragraph from the section Subatomic Time Travel that describes in detail a potential paradox of time travel. And I will explain paradox a little bit more when we're reading, so don't worry about that. So it's just asking to select, and then it says which section from the article confirms that there are still philosophical issues with time travel, like reasons why people think it wouldn't work. Okay, so which of the following sentences from the introduction, that was question 2, which of the following sentences from the introduction, paragraphs 1 through 3, does not support the central idea of the text? So there's a central idea that's developed in those first 3 paragraphs, and which one of these does not support that? And then the next one, question 4, is talking about this summary of the article. Okay, and the summary says, currently there exists debate about possibility of time travel. Certain physicists believe that quantum mechanics make time travel a theoretical possibility, meaning in theory it would be possible. Okay, so adding which of these details would help strengthen this summary of the article? So which of these details would strengthen this summary? That's what that question was asking. Alright, so here we go. Let's get back to the front. I'll probably need to make it a little bit smaller to be able to see most of this. Alright. Again, this one is text 2 in the time travel text set. Time travel may be possible for certain tiny particles, but probably not. Alright, here we go. On June 28, 2009, the world-famous physicist Stephen Hawking threw a party, complete with balloons, appetizers, and champagne. Everyone was invited, but no one showed up. Hawking had accepted that because he only sent out he had expected that because he only sent out invitations after the party had ended. It was, he said, a welcome reception for future time travelers. It was a joke, but it was also an experiment to prove his belief that travel into the past is impossible. Okay, here we go. But Hawking may be wrong. Recent experiments offer some support for time travel's possibility, at least in the world of math. The new study cuts to the core of our understanding of the universe. Proving that time travel is possible would have to change classical physics as well as allow for superfast types of computing that rely on quantum physics, also called quantum mechanics. And I'll come back to that in just a minute after I finish this next paragraph. So, briefly, classical physics deals with the big things like the sun and the moon. Quantum mechanics tells us that the things described in classical physics are affected by things even smaller than atoms. For instance, a ray of light is actually made up of tiny packets of energy. Okay, so here I'm going to have to refer to my notes a little bit because I am not a scientist like Mrs. Dawkins, so I took some notes to share with you. So when we're talking about all this stuff down here, quantum physics and quantum mechanics, we're basically just talking about how stuff works. So physics is science that deals with matter and energy and their reactions. And quantum, well, there's different definitions, definitely having to do with the amount of something, like quantity, okay? But in this case, quantum meaning any of the very small increments or particles into which many forms of energy are subdivided. So basically the smaller divisions of all those tiny little particles. So when we're talking about quantum physics, we're talking basically about how all those little things, like atoms and matter and all that stuff, and how it works. Okay. pretty complex idea, especially for me I do not have a science background, so trust me, I needed the notes too. All right, so now we're going to go into the section called bending space and time. Some think time travel is possible because physics says so. It should be possible based on Einstein's theory of relativity. His famous theory describes gravity as the bending of space and time, which are one thing called space-time. Okay, so he's saying that, again, his famous theory describes gravity as the bending of space and time, and he's saying that that is one thing called space-time. To understand that, imagine that you and a friend stretch a blanket out between the two of you. That blanket is space-time. Space and time are part of the same fabric. Then someone drops a marble onto the blanket and it sinks in a bit. The marble is like a planet or anything with mass. So the mass of planets affects and bends. Whoops, sorry, I didn't mean to move that on you. I was trying to make sure I kept that awake. Okay, there we go. The mass of planets affects and bends both space and time, and with big effects for time. Events that happen at the same time for one observer could happen at different times for another. So, what does it mean for time travel? Instead of the marble bending space-time, imagine a powerful gravitational field. One example would be a spinning black hole. It could make a space-time bend. It could make space-time bend back on itself, creating a closed time-like curve, or CTC. And the reason I'm marking that is because that will be referenced throughout the rest of the text. So whenever you see later CTC, like when that pops up throughout the text, we're talking about this closed time-like curve. Okay, so people could use this loop or tube to travel back in time. All right, so subatomic time travel. Hawking and many other physicists don't like the idea of CTCs, remember, closed time-like curves. Anything traveling through one would create paradoxes. Okay, I'll come back to that in just a minute. So even if you can't go back in time, how can you come back to the future and have it be the same? Okay, and since there's talk of a paradox in this part of the text, and I think it was even referenced in the last one, hint, hint, comparing and contrasting, just wanted to show you my notes I had for us on paradox. We're just talking about, okay, so a paradox is something that is seemingly absurd, sort of like crazy or weird, I guess. Seemingly absurd, like not believable, or self-contradictory, meaning it goes against itself. Contradicting, meaning it goes against something. So a self-contradictory statement or proposition that when investigated or explained may prove to be well-founded or true. So basically something that is superficially unable to be true or false. It can't be true and it can't be false, which is again why it's contradicting. You can see how that could be confusing. So a paradox, something that superficially couldn't be true or false. It goes against common sense, yet it still could perhaps be true. So that's what we're talking about when we're talking about a paradox. Something that seems contradictory and definitely controversial, but could still theoretically be true. So that's what we mean by a paradox. All right, so let's see, back to the text here. Think about paragraph 2 of this section right here under subatomic time travel. All right, here we go. So think about science fiction movies. When someone travels back in time, their actions change the future and may even prevent themselves from being born. Cause and effect fall apart. In 1991, physicist David Deutsch said he knew how to fix paradoxes caused by CTCs. He said that the answer was at the tiniest quantum level. Remember, quantum, we're talking about those tiny, tiny, tiny little particles, probably even smaller than an atom. The key was fundamental particles like quarks, which are inside protons. Physicists believe fundamental particles are the smallest parts of matter. Now they may be made smaller parts, they may be made of smaller parts or not, but we can't see that far. Deutsch came up with a theory to send these particles back in time. Okay, so this guy, physicist David Deutsch, 91, he comes up with this idea to basically test time travel with these tiny little particles. All right, so it's intriguing that you've got general relativity predicting these paradoxes, but then you consider them in quantum mechanical terms and the paradoxes go away, says University of Queensland physicist Tim Ralph. It makes you wonder whether this is important in terms of formulating a theory that unifies general relativity with quantum mechanics. For years, physicists have searched for a theory to unite classical physics and quantum physics. So we're talking about like physical things and things that have to do with how things are made up and space and time and all that. And if you're feeling a little overwhelmed, it's okay. I'm not a scientist either, so we're still going to get the gist of it, and that's what's important. And we're comparing and contrasting this text to the previous one I read. And there are definitely some obvious similarities and some obvious differences. All right, so here we go. It's intriguing. Oh, wait, no, sorry, I read that part. The grandfather paradox. Here we are. Recently, Ralph and his PhD, Ralph meaning this guy up here from University of Queensland, Tim Ralph. So Ralph and his PhD student, Martin Ringbauer, led a team that confirmed much of Deutsch's model of CTCs. Their findings are published in Nature Communications. They investigated how Deutsch's model deals with the grandfather paradox. In the hypothetical scenario, hypothetical, again, it's all in theory, it didn't actually happen. In the hypothetical scenario, someone uses a CTC to travel back through time to murder her own grandfather. In turn, this prevents her own birth. Deutsch's quantum solution to the grandfather paradox works like this. Instead of a human taking a CTC back in time to kill her ancestor, imagine that a particle goes back in time to flip a switch on the particle generating machine that created it. If the particle flips the switch, the machine shoots a particle. The particle back into the CTC. However, if the switch isn't flipped, the machine shoots out nothing. So in this scenario, it is not certain the particle will be shot out. It's just a probability. Probability is sort of like a possibility. Deutsch's big idea was that particles are steady and constant at the quantum level. He insists that any particle entering one end of a CTC must come out the other end exactly the same. Therefore, a particle shot out by the machine with a probability of 1/2 would enter the CTC and come out the other end to flip the switch with a probability of 1/2. By doing so, it would give itself a birth, by doing so, it would give itself at birth a probability of 1/2 of going back to flip the switch. If the particle were a person, she would be born with a 1/2 probability of killing her grandfather. In turn, that would give her grandfather a 1/2 probability of escaping death at her hands. That's good enough in terms of probability to escape the paradox. This strange solution agrees with the laws of quantum physics. Mathematical stunt double. Ralph and Ringbauer simulated Deutsch's model using pairs of polarized light particles, or photons. They say it is mathematically the same as a photon passing through a CTC. We encode their polarization so that the second one acts as kind of a past incarnation of the first. Ringbauer says, so instead of sending a person through a time loop, they created a stunt double of the person and ran him through a time loop simulator. They wanted to see if the stunt double coming through a CTC exactly resembled the original person as he was in that moment in the past. By measuring the polarization of the second photon after it interacted with the first, the team demonstrated Deutsch's theory. Of course, we're not really sending anything back in time, Ralph says. But the simulation, Ringbauer notes, would have remarkable effects for computing based on quantum mechanics. The quantum states of fundamental particles could be cloned, sort of like duplicated. If you can clone quantum states, he says, you can violate the Heisenberg uncertainty principle. Heisenberg's uncertainty principle says certain pairs of things can't be measured accurately at the same time. Basically, the better you know the position of a particle, the less you know its momentum, and vice versa. But if you clone that system, you can measure one quantity in the first and the other quantity in the second. This would allow for advances in quantum computing, such as quantum encryption. CTCs would allow quantum mechanics to perform more powerful computing tasks than classical or even normal quantum computers could do, says Todd Brunn, a physicist at the University of Southern California. But this experiment cannot test the Deutsch model itself. For that, an actual CTC would be necessary. All right, guests from the future, still late. Deutsch's model isn't the only one around, however. In 2011, Seth Lloyd, a physicist at Massachusetts Institute of Technology, tested simulations of a simpler model of CTCs. It resolves the grandfather paradox using quantum teleportation and post-selection. Quantum teleportation is a bit like the teleporter in Star Trek when Scotty beams Spock up from the other planets, but that's where the similarity ends. Speaking of similarities, hint, hint, I believe Star Trek was referenced in your other text. There's another similarity for you. Quantum teleportation only beams around the tiniest bits of information. All right, almost done, guys. Let's see. Post-selection refers to discarding experimental runs where something you wanted to happen didn't happen. Deutsch's theory destroys correlations, Lloyd says. That is, a time traveler who emerges from a Deutschian CTC, meaning one made by that theory of Deutsch, the guy. CTC enters a universe that has nothing to do with the one she exited in the future. Post-selection preserves correlations so that the time traveler returns to the same universe that she remembers in the past. Lloyd's model would make CTCs much less powerful for computing than Deutsch's. However, they would still be far superior to what computers could achieve in typical regions of space-time. Typical computing stores information as zeros or ones. Quantum computing can use 1 and 0 separately or at the same time. Lloyd's model could solve problems at the level of finding needles in haystacks, Lloyd says, but a computer in a Deutschian CTC could solve why haystacks exist in the first place. Lloyd, though, admits how wild the idea of CTCs is. I have no idea which model is really right. Probably both of them are wrong, he says. Of course, he adds, the other possibility is that Hawking is correct, that CTCs simply don't and cannot exist. Time travel party planners should save the champagne for themselves. No guests from the future seem likely to arrive. Okay, so after having read that, I would go back and answer your 4 questions online, and for your assignment, you're creating something to show that you understand comparing and contrasting, like similarities and differences. And you can do a double bubble, which I will have a video to review that as well. Or you could make a Venn diagram or a 3-column chart, or you could write a paragraph explaining similarities and differences. So lots of different options. Let me know if you guys have any questions. Thanks.